Hello, Applied Physics students. Here is the Concept Development Practice page 7.2, Newton's third law. In the example below, the action-reaction pair is shown by the arrows, vectors, and the action-reaction described in words. In A through G, draw the other arrow or vector, and state the reaction to the given action. Then make up your own example in H. So, again, we see fist hits wall, wall hits fist. So, notice, again, in our action-reaction, our vectors are equal in size and opposite in direction. So here's my vector for the head bumps ball. So here's my other vector. And if head bumps ball, then ball bumps head. That's how you state these action-reaction using the interaction rule. So in our next one, here is our vector of the windshield hits bug. So here's our vector for the opposite of that. And if windshield hits bug, then bug hits windshield. So again, here's our vector for bat hits ball. So here's our vector for the ball hits bat. All right, next we have hand touches our nose, which is the vector is here. So here's the opposite vector. Okay. And hand touches nose, so nose touches hand. So here is our vector showing our hand pulls on flower. So here's flower pulls on hand. And again, it becomes flower pulls on hand. All right, on this one, again, here are vectors. So our other vectors are equal in size and in the opposite direction. So we have athlete pushes bar upward. So bar pushes athlete downward. So again, here are vectors. So we have vectors of equal size and in the opposite direction. And we have compressed air pushes balloon surface outward. So balloon surface pushes compressed air. And if it's outward, then this is going to be inward. And here you can draw any picture you would like. It's a basketball and a hand. So ball pushes hand, hand pushes ball. So draw arrows to show the chain of at least 6 pairs of action-reaction forces. So we have tree pulls string and string pulls tree. So there's one set. I have string pulls scale, scale pulls string. Scale pulls string, string pulls scale. Monkey pulls string, string pulls monkey. Monkey pulls string, string pulls monkey. So I've got 1, 2, 3, 4, 5. And now I have man pulls string, string pulls man. All right, so we have Nellie Newton holds an apple weighing 1 Newton at rest on the palm of her hand. The force vectors shown are the forces that act on the apple. To say the weight of the apple is 1 Newton is to say that a downward gravitational force of 1 Newton is exerted on the apple by, again, what exerts the gravitational pull? It's the earth. Nellie's hand supports the apple with normal force N, which acts in the direction opposite W, the weight. We can say N equals W or has the same magnitude as W. We should say it has the same magnitude. It's not equal because it's acting in an opposite direction. But again, N is equal in magnitude, so equal in size, but opposite in direction, the weight, the force of gravity. Since the apple is at rest, the net force on the apple is 0. Okay, so remember, our sum of our forces equals 0 when our object is not moving. Since N is equal and opposite to W, we blank say that N and W comprise an action-reaction pair. So here's where we have to be careful, right? The normal force is the force of the hand pushes apple. This is, okay, the weight is gravity, or we can say, how about if we say the earth, because it's earth that causes the gravity. Earth pulls apple. Now, remember, in all of these that we did, head bumps ball, ball bumps head, right? It was the same two objects in contact with one another. Here I have a hand and an apple, and here I have an earth and an apple. So these, we cannot say that N and W comprise an action-reaction pair. The reason is because action and reaction always blank. They always either act on the same object or act on different objects. Again, they always act on the same object. Head, ball, ball, head. Right? It's the same objects. This is hand, apple, apple, earth. So, the action and reaction always act on the same object. And here we can see that N and W are both acting on the apple or are acting on different objects. Okay? Sorry. They don't act on the same object. They act on different objects. Because we have the head bumps ball and then the ball bumps head. In these, they're both talking about the apple. Okay? So here we can see N and W are both acting on the apple. Sorry about that. So in a correct action-reaction statement, we should have two different objects listed. So in accord with the rule, if action is A acting on B, then reaction is B acting on A. If we say action is earth pulling down on the apple, right? If earth pulls apple, then the reaction is the apple pulling up on earth or Nellie's hand pushing up on the apple. It is the apple pulling up on the earth. To repeat for emphasis, we see that N and W are equal and opposite to each other, and comprise an action-reaction pair, or but do not comprise. They do not, because they're both talking about acting on the apple, but the other object isn't the same. So to identify a pair of action-reaction forces in any situation, first identify the pair of interacting objects involved. Something is interacting with something else. In this case, the whole Earth is interacting gravitationally with the apple. So Earth pulls downward on the apple, call it the action, while the apple pulls upward on the Earth, which is the reaction. Simply put, Earth pulls on apple, action, apple pulls on Earth, reaction. Better put, apple and Earth pull on each other with equal and opposite forces that comprise a single interaction. But for our purposes, this is how we're going to be stating that. Another pair of forces is N, shown, and the downward force of the apple against Nellie's hand, not shown. This force pair is or isn't. So if we have hand pushes apple, and apple pushes hand, that is an action-reaction pair. Suppose Nellie now pushes upward on the apple with a force of 2 newtons. The apple, so here they're equal, and now we're going to add a force to this of 2 newtons. Is the apple going to be in equilibrium or move upward? It's going to move upward, so it accelerates upward. And compared to W, the magnitude of N is, well, it's not the same anymore because we've added to it. Okay. So, and again, it's going to be twice because we're using 2 newtons. And the apple has a force of is a mass of 1 newton. So initially these were 1 newton in size, okay, because it told us the apple was 1 newton up here. So it'll be twice as much. Once the apple leaves Nellie's hand, the force, right, so the hand pushes apple, is 0 because there's no more interaction there. And the net force on the apple is only going to be the weight of the apple, which is going to cause it to accelerate downward because now the Earth pulls the apple and there's nothing counteracting that, so the apple, it will fall down. So important thing here is being able to state these as action-reaction statements. Again, if our hand touches our nose touches our hand. Have a great day. We'll talk to you tomorrow.